This shouldn't exist. Rows of peanut plants, waist-high and flowering, stretching across reclaimed desert in southern Egypt. The sand around them is lifeless. But here, green, thriving, impossible. How did crops designed for rainfall survive in a place that gets almost none? This is the story of one growing season in Egypt's desert reclamation zone. What you're about to see isn't a miracle. It's a negotiation with one of the harshest environments on Earth, and it almost failed completely. We're in the context of Egypt's South Valley development, part of the Toshka project area. This is desert soil, sandy, alkaline, unforgiving. Research describes this region as newly reclaimed land, connected to large-scale efforts to cultivate desert areas where nothing should grow. Peanuts are considered suitable here because they tolerate sandy conditions better than many crops. But suitable doesn't mean easy. It means possible if everything goes right. One growing season, 4 months from seed to harvest, limited water availability in one of the driest regions on the planet. The desert doesn't forgive errors in timing or distribution. Miss a watering window by 12 hours, and entire sections of the field can wilt and die. There's no safety net here, no rain to bail you out, no second chances. The real enemy isn't the heat. Though temperatures regularly exceed 40 degrees Celsius, it's not even the sand, though it drains water like a sieve. The enemy is water itself, or rather, the absolute precision required to deliver it correctly. Peanuts typically need roughly 500 to 700 millimeters of water over the growing season for good yields in rain-fed conditions. Here, there is no rain. Zero. That means every single drop has to be engineered, delivered, timed, and monitored with surgical precision. Too little water and the plants wilt, roots fail, growth stops. Too much water, and you create salt crust on the surface, suffocate the roots, and waste a resource you can't afford to waste. The desert punishes both mistakes equally and immediately. There's another problem. Water doesn't just need to arrive, it needs to arrive uniformly. If one section of the field gets 15% less water than another section, you'll see the difference in plant health within 3 days. By 2 weeks, those plants are beyond recovery. So why grow peanuts in a place like this? Why not something simpler, more forgiving? The answer is economics and biology working together. Peanuts are a cash crop, valuable both domestically and for export. Global demand is consistent. They're also nitrogen fixers, meaning they actually improve marginal soil over time rather than depleting it. And their root structure, while demanding about water, can handle sandy conditions if the irrigation system works perfectly. The seeds go into carefully prepared ridges. Spacing is precise, calculated for maximum efficiency. Soil texture matters enormously. Everything is measured. Nothing is left to chance. This isn't traditional farming by instinct or experience. This is farming treated like engineering, like building a bridge or designing a water treatment plant. The infrastructure comes first, before a single seed touches the ground. Pumps pull water from deep wells or allocated canal sources. Distribution lines run the length of each field section, branching into smaller lines, then individual emitters. Drip irrigation systems, or controlled flood systems, deliver water directly at root level, minimizing evaporation losses in the brutal heat. Every morning starts with pressure checks across the entire system. Every evening ends with soil moisture readings, taken at different depths, across multiple points in the field. Uniformity is everything. The team uses soil probes and moisture meters to verify that water is penetrating to the correct depth. If the readings show variation between zones, adjustments happen immediately. Timing follows the plant's growth stages with precision. Early on, shallow watering to establish the root system without waterlogging. Mid-season brings deeper watering during the critical flowering and peg formation stage. This is when the plant does something remarkable. After pollination, the fertilized flowers actually bend down and push themselves underground to form the pods. Late season requires controlled reduction of water to firm up the pods and avoid rot before harvest. For 6 weeks, the system worked flawlessly. Plants emerged uniformly. Growth was strong and consistent across all sections. The canopy developed evenly, a deep green against the pale sand. Then the field started failing, and it happened fast. The western section showed stress first, leaves curling inward, a defense mechanism against water loss. Growth visibly stunted compared to the day before. Within 3 days, entire rows were wilting, while the eastern half of the field looked completely healthy. The team checked everything. Weather data showed no unusual heat spike. The watering schedule had been followed exactly. Water supply from the source was normal. Then they walked the field and saw it. White salt crust forming on the soil surface in patches. Uneven wetting patterns. Some areas bone dry while others were muddy. The distribution system had developed blockages over time. Some emitters were clogged with mineral deposits from the water. Others were delivering inconsistent flow due to pressure variations in the lines. The result was a disaster in slow motion. Parts of the field were being overwatered, pulling salts from deeper in the soil profile and depositing them at the surface, where they formed a toxic crust. Other parts were being starved of water entirely, with plants slowly dying of thirst just meters away from flooded sections. This was happening 2 weeks before the critical flowering stage. If the stress continued, the plants wouldn't have the energy to form flowers. No flowers meant no pollination. No pollination meant no pods forming underground. The entire season would be lost. They diagnosed the problem like engineers, not farmers hoping for better luck. The team walked every single row, marking the dry zones with flags, mapping the oversaturated areas, measuring the actual water delivery at hundreds of points. They pulled emitters one by one, flushed the distribution lines section by section, replaced every clogged component they found. Then came the scheduling adjustments. They shortened watering intervals in the underwatered zones to help plants recover faster. They reduced volume in the oversaturated areas to let the soil drain and allow oxygen back to the roots. They added a calcium treatment to the worst affected zones, helping to leach the accumulated salts below the root depth where they couldn't harm the plants. It wasn't dramatic. There was no single brilliant insight or revolutionary technique. It was methodical, systematic problem solving. Check the system. Identify the failure points. Correct them. Monitor the results. Repeat. For 5 days after the fixes were implemented, nothing visible changed. The stressed plants looked the same. The team kept monitoring, kept adjusting, trusting the process even without immediate proof it was working. On day 6, new growth appeared. Small, but unmistakable. The stressed plants were responding. Leaves began to darken to their proper color. Turgor pressure returned, leaves flattening out instead of curling. Canopy density started evening out across the field. Dry sections began to match the healthy sections. 2 weeks later, flowers emerged, yellow blooms appearing uniformly across rows that had been dying. That's the signal every grower waits for. Flowers mean the plant is healthy enough to reproduce, that it has the resources and strength to create the next generation. After pollination, those flowers perform their strange downward journey, pegs pushing into the soil to form pods in the darkness underground. The field had recovered because the fix addressed the root cause, not the symptoms. Water distribution uniformity. Not hope, not luck, not prayer. Measurement, correction, and relentless monitoring. 4 months after planting, harvest day arrived. Specialized equipment moves through the rows, pulling the plants and exposing the roots with their clusters of pods clinging to them. Workers shake the pods free, sort them by size and quality. The proof of success isn't in a single number or yield statistic. It's in the physical result you can hold in your hand. Pods that are firm, fully filled, uniform in size and quality. Visual evidence that the system worked. That precision irrigation in a zero rainfall environment can produce a commercial crop. This field produced a successful peanut harvest in a place that receives virtually no rainfall, in soil that was pure sand and mineral deposits just years ago. Not because the desert was conquered or transformed into something it's not, but because every variable was identified, controlled, and monitored. Growing peanuts in reclaimed Egyptian desert isn't about transforming sand into paradise or performing agricultural miracles. It's about building a system so precise, so well monitored, so responsive to problems that even a hostile environment has to cooperate. Water discipline, soil strategy, distribution uniformity, relentless monitoring, rapid response to problems. That's the formula. Miss one piece, and the desert wins. Get them all right, and crops grow where nothing should survive. This field exists because someone treated farming like infrastructure, like a system that needs constant attention and maintenance. And infrastructure doesn't run on optimism or good intentions. It runs on standards, on measurement, on the willingness to fix problems immediately when they appear. If you want to see more stories about what actually works when conditions say it shouldn't, subscribe. We don't cover hype or exaggeration. We cover the real systems, the actual methods, the unglamorous truth about how impossible things become possible.